Welcome to Chapter 1 of the Introduction to Spectroscopy series. In this chapter, we'll explore the fundamental principles that underlie all spectroscopic techniques. Spectroscopy is essentially the study of how light interacts with matter, and it provides one of the most powerful tools available for understanding molecular structure and composition. We'll examine the electromagnetic spectrum, energy quantization, and the basic processes of absorption and emission that make spectroscopy possible. At its core, spectroscopy is the study of light-matter interactions. When a photon with energy E equals h times nu approaches a molecule, three possible outcomes can occur. Absorption, where the molecule takes in the photon's energy. Emission, where the molecule releases energy as light. Or scattering, where the photon is redirected. These interactions depend on the photon's wavelength and the molecule's structure, forming the basis for all spectroscopic analysis techniques. The electromagnetic spectrum spans an enormous range from gamma rays to radio waves. Different spectroscopy techniques utilize different regions. UV-visible spectroscopy uses 200 to 800 nanometers to probe electronic transitions. Infrared spectroscopy targets molecular vibrations at 2.5 to 25 micrometers. Microwaves probe molecular rotations, while X-rays examine core electrons. Each region probes different molecular properties, giving us complementary information about molecular structure. Energy quantization is the cornerstone of spectroscopy. Molecules can only exist at specific, discrete energy levels. The relationship E equals h times nu tells us that photons can only be absorbed or emitted when their energy exactly matches the gap between molecular energy levels. Planck's constant h and the speed of light c are universal constants that govern these interactions. This quantization is why each molecule has a unique spectral fingerprint. In absorption spectroscopy, molecules in the ground state absorb photons and transition to excited states. The Beer-Lambert law, I equals I naught times e to the negative alpha L, describes how light intensity decreases as it passes through a sample. Writing the absorption coefficient alpha as the molar absorptivity epsilon times concentration gives the familiar form: absorbance equals epsilon times concentration times path length, and that is what makes quantitative analysis possible. Absorption spectra show peaks at wavelengths where molecules efficiently absorb light. Emission spectroscopy captures light released when excited molecules return to lower energy states. Fluorescence occurs rapidly, within nanoseconds, while phosphorescence takes microseconds to seconds because it emits from a triplet state through a spin-forbidden transition. The Jablonski diagram illustrates these pathways, showing absorption, internal conversion, and various emission processes. The Stokes shift describes how emitted light almost always has a longer wavelength than absorbed light, due to energy losses during relaxation. Not all transitions between energy levels are allowed. Selection rules derived from quantum mechanics determine which transitions can occur. For UV-visible spectroscopy, the electric dipole moment must change. For IR spectroscopy, the dipole moment must change during vibration. For Raman spectroscopy, the polarizability must change. These rules explain why certain molecules are visible to some techniques but invisible to others, making different methods complementary. Molecular complexity directly determines spectral complexity. Simple diatomic molecules like nitrogen have exactly one vibrational mode, and because nitrogen is homonuclear, that mode is infrared inactive. It shows up only in Raman. Bent triatomic molecules like water have three vibrational modes, from 3n-6, and correspondingly more peaks. Complex organic molecules like glucose have many functional groups and produce rich, overlapping spectra. Understanding this structure-spectrum relationship is key to interpreting spectroscopic data and identifying unknown compounds. Multiple spectroscopy techniques exist, each probing different molecular properties. UV-visible examines electronic transitions. IR and Raman probe molecular vibrations through different mechanisms. NMR investigates nuclear spin environments. XBS analyzes core electron binding energies. Mass spectrometry measures mass-to-charge ratios. Choosing the right technique depends on what molecular information you need. Often, combining multiple techniques provides the most complete picture. Let's recap Chapter 1's key concepts. Spectroscopy studies light matter interactions. Energy is quantized according to E equals h nu. Absorption promotes molecules to higher energy states, while emission releases photons. Selection rules govern which transitions are allowed. Molecular structure determines the spectral fingerprint. In Chapter 2, we'll dive into UV visible spectroscopy, exploring electronic transitions and the Beer-Lambert law for quantitative analysis.